You're watching a Channel 98 NBISD TV production.
Hi, welcome to another fantastic episode of That Geometry Show. As always, I'm your peachy keen host, Kevin Corpy. Today's show is going to be Circles Part 2. We're going to be finishing up what we started last time. But today we're going to be inscribing things inside the circles, which sounds a bit dangerous, but believe me, it's much safer than dividing by zero. We never do that. Okay, so if you haven't already, download those worksheets from the district website. Get them out in front of you, play along with me at home, and let's do some math together. Lesson 28 is all about circles, arcs, chords, inscribed angles, and we're going to look at area at the end. And if you've got your textbook in front of you, you want to turn to chapter 9.3 and 9.4. Now last week we did look at circles, and we learned how to find the degree measure of an arc. And the degree measure was different from the length of an arc. And that's what we're going to kind of look at today. But to review, the degree measure of an arc of a circle is the same as the degree measure of the intercepted central angle. For instance, in this circle P, we have circle P, there's the center. We know that segment PR, which is the radius, is 9 inches. And the measure of QPR, which is this right here, QPR, it's a 3-letter designation. We know that this is 40. Then we know also that the measure of arc QR, this here, is also 40, and that's 40 degrees. So the arc measure is the same as the intercepted central angle. Now that's different than what we're looking at today. Sorry, the arc length, not arc measure, we use the letter S to denote it, and it is a linear unit. It's going to be a fraction or a part of the circumference of the total distance all the way around. And it does have something to do with the central angle. Just like the central angle is a part of our full 360-degree rotation, the arc length is going to be a fraction or a part of the entire distance around, or the circumference. So let me show you how to set that up. When you're setting up proportions, it's real easy to set them up if you think part to whole equals part to whole. So I've put those key words in here. We're going to look at a part of the circumference, which is our arc length, to the whole circumference, and that's going to be proportional to the degree part of the circle, which is our central angle, to the degree of the entire or the whole circle. So part to whole, part to whole. So let's go ahead and plug in. The part of the circumference is our arc length, that's S, is to the whole circumference, which we know is 2 pi r. The part of the circle is the central angle, and the degree of the whole circle all the way around is 360 degrees. Now remember from the previous page that the radius was 9 inches. We're going to need that for this calculation. So I'm going to go ahead and plug in. The arc length is S, we use S. Is to 2 times pi times 9, and that's going to be inches, is proportional to the central angle, which remember was 40 degrees, to the entire 360 degrees, which is a constant. So now I've set up a proportion. I have one unknown S. I can actually solve for S. I'm going to solve this equation by simplifying on this side. If you have trailing zeros, you can kind of divide them out. So I really have 4/36, which simplifies to 1/9. And over here I have S, my arc length, all over 18 pi. So if I multiply both sides by 18 pi, I get S equals 18 pi divided by 9, which is 2 pi. And 2 pi is approximately 6.283. And because I had inches in the original problem, I'll put inches here. So that would be the length, not the measure. That is, if you started at point Q, and you traveled around the curve all the way to point R where your friend lives to go do your math homework, you will have traveled 6.283 inches, and you'd be probably freaking out at how close your friend lives to you if that was the actual distance. Okay, so given a circle now, we can do other things with it. We can inscribe either a polygon or an angle. And we're going to look at polygons first. Remember, a polygon is just a closed geometric surface where the points or the line segments meet at things called vertices. And we can stick those inside of a circle. So we're going to start with the circle of a predetermined size, and then we're going to put inside or inscribe a particular polygon. For instance, This polygon here has 1, 2, 3, 4, 5 sides, and so we call it a pentagon. And remember, we label the pentagon by the consecutive points that are the vertices. So we can call it polygon or pentagon A, B, C, D, E would work. It is inscribed inside this circle. Okay? Notice that the segments of the pentagon or the polygon in general actually are chords of the circle. And we talked about chords last time. A chord is any line segment whose endpoints lie on the circle. And we also want to notice something else here. If I look at one of these chords that is the side of a polygon, that actually defines an arc as well. So last time we looked at arcs being defined by a central angle, a chord as well, or a side length of an inscribed polygon, also defines an arc. Okay? So there's several ways to define it. We just need to look at the picture and kind of see what we have. Now we're going to look at some theorems that relate to chords and inscribed polygons. The first theorem is going to relate the minor arcs, which remember is an arc that's less than a semicircle, less than 180 degrees, to the respective chords that define it. And here's the theorem. In a circle, or in congruent circles, two or more arcs are congruent, which remember means they have the same length, if and only if their corresponding chords are congruent. Well, let's review the if and only if. That means it's bidirectional. One side implies the other. So if I have congruent chords, I have congruent arcs. If I have congruent arcs, that implies that the chords are congruent. So if I have any circle at all, let's say that I have this chord right here, and I have another chord over here that maybe is slightly tilted. And if I know that those two right there happen to be the exact same length, then I know that these arcs right here that correspond to those chords are also congruent to each other. They might have a different length than the chords. They will. They'll be a little bit larger, but they will be congruent to each other. All right, let's put that theorem to work here in this example. In the circle, we know that the measure of arc, remember the arc has kind of a little arc above the two-letter distinction, of arc WX right here is 30, so I'm going to label it. And the measure of arc XY is 50, so this one here is 50. And the measure of YZ arc right here is also 30. We want to find we also know that WY is 14. Well, on the diagram, WY is a chord that connects one part of the total arc to the other part. Now, based upon that information, we want to figure out what XZ's measure is, what the length of XZ is. And that's going to be right here. So let's identify it. We want to know what that is. Well, let's see. How can we do that? We can look at our picture, and we know that the measure of arc WXY, which basically corresponds to the arc or the chord WY, and I'll put 3 letters there so I know which direction I'm going, is going to be the sum of the other two arcs. So it's going to be 30 from WX and 50 from X to Y. So 50 plus 30 is 80. And I also can look at the measure of arc XYZ, which extends from here to here to here. And that is the arc that corresponds to the segment that I'm trying to find, XZ. And its sum is going to be the sum of arc XY, which is 50, plus YZ, which is 30. So it also equals 80. So these two different arcs actually are the same measure, so we know they're congruent. So the theorem tells us that the two chords that they correspond to, namely WY and XZ, the one we're trying to find, are congruent. So knowing that, we know that XZ is the same measure as WY, which was given to be 14. So we're stringing along these little logical steps in order to be able to use our theorem. Okay? Let's look at another theorem. This is an important theorem that relates the circle's diameter to a very, very special chord. And here it is. It says, if a diameter is perpendicular, that means forms a right angle at 90 degrees to a chord, then it bisects the chord and its arc that corresponds to it. Now remember, bisect means to cut in half. All right? Let's look at this example here, and I'll show you what I mean. In this circle, if we know that segment GF, which spans from here to here, is a diameter. Now, a diameter is a chord, but this is a special chord because we know if it's a diameter, it passes through the center, which is very important. We want to find the value of x. Okay, well, how is that going to help us? Notice that the diameter here intersects this chord. And we don't have labels on this chord. If you want, you can call it chord AB or line segment AB. But also notice that this little symbol right here in red shows us that this diameter and this chord form a right angle to each other, so they are perpendicular. So by the theorem, we know that this diameter bisects segment AB, so that this length right here and this length here are the same measure. We also know from the theorem that the arc that corresponds to this line segment, AB, is also cut in half precisely by the diameter, so that this arc length from A to G is congruent to the arc length from G to B. But in this specific example, we don't really need to concern ourselves with the arc lengths. We want to look at the lengths of the chords themselves. So we could take our expressions there, 4x plus 5, and we know it has to be congruent, so they have the same measure as 33. Now we've set up our little algebraic equation, and all we have to do is solve. So I'll subtract 5 from both sides, and I get 4x equals 33 minus 5, which is 28. Dividing both sides by 4, and we get x is 7. And there's no units up here, so we don't have to worry about calling it inches or anything. Okay, so memorizing the theorems is a good idea, because if you know what the theorem is, even if you can't recall it right away, you know that it exists, and so you know that you can use it. All right, and there are a lot of theorems today. Here is another one. This one's in purple. All right, two chords are congruent in a circle if and only if. So again, this means it's bidirectional. One's going to imply the other. If and only if those two chords are equidistant, the same distance from the center. Okay, let's look at an example and we'll put it to use. In this circle right here, which we're calling circle M, we name it by the center, we know that AB, segment AB, and CD right here are parallel. It's given in the instructions, and remember these little red arrows, or they don't have to be red, on the line show that they're going in the same direction. That means they're parallel in Euclidean geometry. Okay, we also know that segment AB is congruent to CD. Well, what are those? That means that this segment here and this segment here are the same measure, the same length. Well, now here comes the what ifs. If the length of MP, which is this right here, happens to be 3 units, and we know that CD, which is this entire thing right here, happens to be 8 units, we want to know what the radius of the circle is. Whoa! The radius of the circle, well, that's not really even drawn on this picture yet. So we're going to have to figure out how we can do that. The easiest way to visualize the radius is to draw it. Now I'm going to draw a very specific radius that comes from the circle to over here, to point C. And I did that because I know what the measure of CD is. Okay, well, let's see if we can use the theorem here. Two chords are congruent if and only if they're the same distance from the center. And the last theorem we had said that a diameter bisects the chord. Well, if I extend this line segment PQ that goes through the center, if I extend it in all directions, it is a diameter. So I know that it actually bisects these two chords, which are parallel to each other. So I know that all of these lengths right here are the same. Well, now that I know that the length of CD, the whole thing is 8, and this diameter here bisects it, I know that this length right here is 4 units, right here. That's 4, okay? Now, I know that these are parallel and this bisects it, so from the theorem we just had, it says two chords are congruent if and only if they're equal distance. Well, we know that these chords are congruent, so that implies that they're the same distance from the center. So if we know this one is 3 units from the center, because that was given, then we also know that this one is also 3 units from the center. So I have a 3, a 4, and remember that it's a perpendicular bisector, the diameter is, so we have a little right angle there. Well, I'm going to redraw what we have there off to the side because it's getting kind of cluttered. But essentially, we have a right triangle right in here. And we know that one of the short legs is 4, and this leg is 3, and the radius, which is right here, is the hypotenuse, and that's what we're trying to find. So we have now set it up so we can use the Pythagorean theorem. So let's go ahead and plug in. The two shorter legs go first, so 3 squared plus 4 squared equals r squared. And so I get 9 plus 16 equals r squared. 25 equals r squared. And we'll take the square root. And the square root of 25, usually we take plus or minus, but we're talking about a radius, and radiuses are positive. Radii are positive. And so we get 5. So we actually had to use 2 theorems there and have a plan of attack to find our radius. But drawing on the picture and marking things that you're given is going to help you develop a successful plan. All right, one last example here before our break. We want to take this circle and find the length of NT. Well, NT is this right here. So if we look at our theorems, we know that this chord and this chord here are the same distance from the center because we have these 2 line segments that are drawn with the little line here. So we know that these are congruent. We also know that if I extend this line here through the center, I get a diameter which bisects this segment here, which started off as 22. So I know that this right here is congruent to that, which has to now be congruent to that, which has to be congruent to that. They're all the same measure. I'm going to put double tick marks there because they're different from this right here. So if they're all equal to each other and they're all equal to half of 22, they're all equal to 11. So NT is 11. All right, this is a good time to take a quick break, watch some public service announcements, and I'll be right here waiting for you when you get back. I'm a man of my word. I'm here waiting for you. Are you there? Okay, let's get right back to circles. All right, not only can we inscribe polygons into a circle, but we can also inscribe angles. So here's the definition. An inscribed angle has its vertex on the circle, and the 2 sides are chords of a circle. So in an inscribed polygon, we have the vertices on the circle, and if we just look at the polygon itself and take one of the angles that forms the polygon, we have the vertex of the angle on the circle itself, and then the 2 sides of the angle form chords. So we have chord AB right here, which is a line segment, and then right here we have chord AE. So that would be an inscribed angle. So it's kind of a component or a part of the inscribed polygon, but we can look at them separately. All right, so all of the angles in this inscribed polygon are going to be inscribed angles. Here's another one. Inscribed angle BCD. Again, this is not a central angle. This has a vertex on the circle itself. A central angle has a vertex on the center of the circle. Okay, now, each of these inscribed angles has an intercepted arc. For example, if I look at the intercepted arc of angle EAB, which is right here, EAB, it forms this major arc, which comes all the way around. And so we have to use a 3-letter distinction. So I can call it arc ED, and then the finishing point. So starting point, some middle point, and the ending point. Or we can also use C as the intermediate point, arc ECB. But it's a major arc. Now, the question is, can we tell anything about the intercepted arc from its corresponding inscribed angle? But of course we can. It's geometry. Things all kind of fit together. Here is the conclusion of that. If an angle is inscribed in a circle, then the measure of the angle equals 1/2 the measure of the intercepted arc. Or we can say the arc's measure is twice the angle's measure. So for example, if I'm looking at this right here, and I know that this angle measure, for instance, is, let's call it 100 degrees, then I know that the arc that's formed by it, that whole thing right there, is going to be twice the size, or 200. Okay? So 100, 200. The arc is bigger than the inscribed angle. So you can say that the angle is half the size of the arc, or the arc is twice the size of the angle. Let's look at a specific example. If P is the center of this circle, we want to find, of course, the value of x. So P is the center. That's good to know, so that we automatically know that CB is the diameter. And we're trying to find the value of x. So what do we have? We have this right here, which is a central angle, and we have this right here, which is an inscribed angle. And notice that they both subtend the exact same arc. Both of those subtend this arc right here, arc AB. Okay, so last time we learned about how the central angle is related to the arc. It's actually the same measure, and today we learned that this angle is half the measure of the arc. Well, basically, I'm given information about the size of those two angles. So I can set up the equation. Since they both have to equal the measure of the arc, I can actually set them equal to each other. But I'm going to do that in two steps. So I'm going to say that the measure of arc AB is equal to 4x plus 4. Okay, because that's the central angle. I can also say, very carefully here, that the measure of arc AB is equal to 2 times 3x minus 21, which is this angle down here. Now, since they're both equal to the measure of AB, I can set those expressions equal to each other. So here's the magical step. 4x plus 4 equals 2 times 3x minus 21. And we have several options here. I can distribute the 2 on the right-hand side, but since everything on this side is divisible by 2, I'm going to divide both sides by 2. So I get 2x plus 2 equals 3x minus 21. And I'll bring the x's over here and the numbers on the right. So I get x equals 21 plus 2, which is 23. Okay, and that's actually going to be in degrees because I'm talking about degree measures. So we use two theorems. We use the central angle, who's the same measure as the arc, and the inscribed angle, because it has a vertex on the circle, and the new theorem from today, saying that it was half the size of the arc. Getting them both in terms of the measure of AB, and once they're equal to each other, both measured to AB, we can set them equal to each other. We get one equation with one unknown, and we've reduced this geometry problem to an algebra problem. Okay, one last important theorem for today. Here's the theorem. If an inscribed angle of a circle intercepts a semicircle, which is neither a major arc nor a minor arc, remember it's 180 degrees, half the circle, then the angle is a right angle. That's pretty fascinating. Let me show you what I mean. In this circle, if NR is a diameter, and that's important because it passes through the center. Now, a diameter always bisects the area of a circle. So I have a half circle or a semicircle up here and a semicircle down here. So notice now that I have an inscribed angle, angle NMR. Here's N, there's M, and here's R. So it is an inscribed angle because its vertex is on the circle, and so are its endpoints, and the two sides of the angle are going to be chords, line segments. So what we know now from the theorem is that this is a semicircle, and here's an inscribed angle forming a semicircle. We know that this right here, the measure of angle NMR equals 90 degrees. It's a right angle. So let's read the question now. If we know that MR right here is 12 and the circle has a radius of 10, which means this distance is 10 and this distance is 10 on either side of the circle, we want to find the measure of segment NM. Well, you're probably already at home jumping up and down because you know which theorem we're going to have to use. The right angle in a semicircle also creates a right triangle whose diameter is the hypotenuse, and we know one of the short legs and we're trying to find the other short leg. So we can set it up. Let's go ahead and do that. Segment NM, the one we're trying to find, squared, plus the other short side squared, 12 squared, equals, and this is the only place we really have to be careful, we were given the radius. The diameter is then twice the radius, or 20 squared. And it's opposite the right angle, so it's opposite the other two shorter legs on one side of the equation by itself. Again, we've taken a geometry problem, we've reduced it to an algebra problem, now we just have to do the math. So if I square both the numbers, I get NM squared equals, plus, we'll do it in two steps, plus 144 equals 400. And then I subtract, so segment MM squared equals 400 minus 144, which is equal to 256. And if I solve for NM by taking the square root of both sides, I get NM, the measure of NM, is 16 units. So I have a right triangle that's a 20 by 12 by 16. Okay, and that's using the special property. An inscribed angle in a semicircle always forms a right angle and therefore also forms a right triangle. Now it's time for my favorite part of the show. It's the Say What section. Oh yeah. And I know you might be getting tired of Archimedes, but I never do. And he just so naturally lends himself to all these geometric discussions we're having. I'm not trying to force him in, he's just there. Okay, today we're talking about the area of a circle on the Say What portion. The area A of a circle is a measure of how much space it takes up in a plane. Okay, not an airplane like it has to fit in the overhead compartment. Of course, we're talking about the two-dimensional plane. Okay, its formula is given by the following formula: area equals pi times r, the radius, squared. Okay, so again, all we really need to know for the area to figure out the amount of space it takes up is the radius. Now, we've used this formula on previous episodes, but I know everyone out there is probably at least a little bit curious, if you have been asking out loud, where do all these formulas come from? Do they fall out of the sky? Do they grow on trees? Do people trip over them and pick them up and say, oh, look at that? No, they're actually discovered by brilliant mathematicians throughout the history of math. This one supposedly was first discovered by the man Archimedes. Now, there's a story behind it, and I'm going to tell you the story here. One sunny afternoon, two guys, Kyle and Wendy, were ancient toga tailors, and they asked Archimedes if he was interested in walking down to a very popular pizza party in downtown Syracuse, Sicily, for lunch. See, Kyle and Wendy wanted to repay Archimedes for his kindness in helping them develop a lightweight yet durable toga material that left the wearer cool in the summer and warm in the winter. A perfect toga material. Now, even though Archimedes was extremely busy with his math and his circles, he didn't want to upset his new friends. He didn't have that many. So he accepted their lunch invitation. So they placed an order at the pizza parlor for a 14-inch round pizza. And remember from last episode, that means 14-inch diameter. Pretty big pizza. But just as it was served, Kyle and Wendy got summoned on a service call. It was a toga emergency. So they immediately jumped from their seats to answer the call for comfort, leaving Archimedes alone by himself with the pizza. Now, what would you do? Well, Archimedes wasn't interested in service calls, and he wasn't really that hungry, so he calls out to the chef, "Hey, Rossetti, bring me a big, sharp knife." Not only does the chef oblige, but he watches in horror while Archimedes begins to cut up the round pizza into very thin slices, like this. Now, each slice of pizza is going to be uniform when he cuts it up, and the slices are going to be even in number, because as we slice across like this, we always have a slice that's on top and a slice that's opposite on bottom. So we're going to end up having pairs, so we're going to have an even number of slices. Now, here's Archimedes playing with this food. He takes these slices, and he notices that if he slides them side by side and takes two at a time, he gets something that looks almost rectangular, like this down here, two slices. And he also knows that if he slices them thinner and thinner, it looks even more and more like a rectangle. So let's think what we have here. If we take half of them on top and half of them on the bottom, then each of those are going to be half the circumference. If the circumference is 2 times pi r, half the circumference is pi r. So that forms one of the dimensions of our rectangle. And what is the height? Well, the height of the rectangle is just the radius of the pizza, or the radius in general. So I have something that approaches a rectangle with dimensions of pi r times r. And the area of a rectangle was known. You just multiply the two side lengths together. So here's the brilliance. Pi r times r is pi r squared. And that is how the formula for the area of a circle came to be. So voila, there it is. It's fun to be brilliant. So imagine if Archimedes' mother had told him not to play with your food, Archimedes, instead of a brilliant mathematician who is finding equations and formulas for the area of a circle, we would just have another math guy eating pizza. And we don't need any more of those guys, do we? Thanks for joining me today. Remember, you can always email me if you have any questions about today's episode, or if you got a good pizza recipe. Until next time, I'm Kevin Corpy, and I'll catch you on the flip side.